So what is light? You'd think that's a simple question, right? I mean, it's literally how we see everything. But for hundreds of years, that one question started one of the biggest arguments in all of science. It put some of the greatest minds in history head to head. Is light a stream of tiny particles? Or is it a wave, kind of like a ripple in a pond? Let's get into it. This is light's ultimate identity crisis.
Back in the 17th century, you had a real heavyweight matchup. In one corner, repping Team Particle, you had the absolute legend, Sir Isaac Newton. His whole idea was that light is made of these tiny little bullets he called corpuscles. And in the other corner, for Team Wave, you have the Dutch genius Christian Huygens. He was convinced light acted just like waves on water. So two brilliant guys, two completely opposite ideas.
Now, for more than 100 years, Newton's idea was king. It totally dominated the scene. And you can't really blame people. I mean, when the guy who figured out gravity and motion tells you how light works, you're probably going to believe him. His particle theory just seemed to explain the world so perfectly. Newton's big idea was called the corpuscular theory. And honestly, it just makes sense, right? It explains why light seems to travel in perfectly straight lines and why shadows have such sharp, crisp edges. A stream of little particles would do exactly that. It also gives a really simple explanation for reflection. The particles just bounce off a mirror like tiny little billiard balls.
So his theory was great for the basics, but it had this one little hidden detail, a prediction that you could actually go out and test. To explain why light bends when it goes from air into water, Newton's model needed those little particles to actually speed up. He figured the denser water would pull on them harder. Now, remember that prediction. Tuck that away. It is going to become super important in a little bit. But while Newton's theory was the talk of the town, Huygens was cooking up something totally different. He was saying, hey, what if light isn't a particle at all? What if it's a wave? This was a pretty wild idea at the time, and it went against everything the great Newton was saying.
To really get what Huygens was talking about, you have to understand this one idea, the wave front. And don't worry, it sounds way more complicated than it is. Just picture dropping a stone into a calm lake. You see those perfect circles spreading out? Each one of those circles is a wavefront. It's just the line connecting all the parts of the wave that are at the exact same point in their vibration. And this is where Huygens' genius really shines. He came up with this principle. He said, okay, imagine that every single point on one of those wavefronts is its own little mini source, sending out its own tiny little wave, or a wavelet, and if you just draw a line that connects the edges of all those new little wavelets, you can predict exactly where the bigger wave is going to be a moment later. It's such a clever and powerful way to see how waves move. So, using this idea, Huygens could perfectly explain reflection. His model showed exactly how an incoming wave would bounce off a surface. And guess what? It predicted that the angle it comes in at is the exact same angle it bounces off at, the same law that Newton's particles explained. But here it is. This is the moment of truth, the real test. When Huygens used his principle for light bending as it enters water, his model made the exact opposite prediction to Newton's. For a wave to bend the way light does, it absolutely must slow down. So now the stage is set, you know? You've got two theories, they both explain the same stuff, but they make opposite predictions about something you can actually measure, the speed of light. So for over 100 years, the debate was kind of at a stalemate, mostly because, Newton was Newton. But science isn't about who has the bigger reputation. It's about evidence. The hunt was on for that one single experiment, that smoking gun, that could finally, once and for all, prove who was right. And that was the big problem, wasn't it? If both models work for the obvious things, how do you pick a winner? You would have to find some weird behavior that only a wave could do, something a particle just couldn't. And the answer turned out to be something called interference. Let's go back to those ripples in the pond. If two wave crests meet, they join up and make an even bigger wave crest. That's constructive interference. But if a crest meets a trough, they cancel each other out, and for a split second, the water is flat. That's destructive interference. This whole adding and subtracting thing is a signature move of waves. Particles just don't do that. They just bounce off each other. Then, in 1801, a guy named Thomas Young did one of the most brilliant and famous experiments in all of physics. He took a screen with two tiny little slits in it and shone light through them. Now, if light was a particle, you'd just get two bright lines on the wall behind it, right? But that's not what he saw. He saw a whole pattern of bright and dark stripes. That pattern was the undeniable fingerprint of interference. This was it. This was the smoking gun. Case closed. Light had to be a wave. As if that wasn't enough,
There was even more evidence piling up for team wave, and this clue was called polarization. Okay, so light is what we call a transverse wave. That just means it vibrates up and down or side to side at a right angle to the direction it's actually traveling. And because of that, you can filter it or polarize it so that only the vibrations going in one direction get through. You can't do that with other kinds of waves, like sound waves. So think of it like this. Normal light from a lamp or the sun is unpolarized. It's just a jumble of vibrations going in every direction. But when you pass it through a special filter, a polarizer, it gets organized. It becomes plane polarized. All the vibrations are now lined up, going in the same direction. And this isn't just some weird thing that happens in a lab. If you own a pair of polarized sunglasses, you use this every day. That annoying glare that bounces off a wet road is actually light that's been horizontally polarized. Your sunglasses have a vertical polarizer that acts like a gate, and it blocks that specific horizontal glare, which is why you can see so much more clearly. And that trick only works because light is a transverse wave. So, that's it, right? Case closed. Team Huygens for the win. Newton was wrong. Light's a wave. Let's all go home. Well, not so fast. The story of light was about to get another, even stranger plot twist. A twist that neither of these geniuses could have ever seen coming. Let's just quickly recap this crazy journey. In the 1600s, the big debate kicks off. In 1801, Young's experiment seems to prove wave theory for good. And for a solid 100 years, that was the final answer in every textbook. But then, the early 1900s happened, and Albert Einstein, while trying to solve a completely different puzzle, had to suggest that light energy comes in these little, distinct packets, these particles. He called them photons. And just like that, the particle was back. So after all that debate, all that fighting, who was right? Newton or Huygens? And the completely bizarre, mind-bending answer from modern physics is they both were. Light has a dual nature. In some experiments, it acts exactly like a wave. And in other experiments, it acts exactly like a particle. It's not one or the other. It is somehow impossibly both. This whole centuries-long quest to understand something as simple as light ended up showing us that the universe is way stranger than we thought. And it really makes you wonder, doesn't it? If we could be so wrong for so long about something as basic as light, what other fundamental things about our reality are we missing right now?